Welcome to the Additive Snack podcast. I'm your host, Fabian Alefeld, and today we have a very special guest with us, Chuck Hansford, Director of Advanced Development at Tecomet. Welcome, Chuck.
Hi, good morning.
So, Chuck, I don't think I'm exaggerating if I say you're one of those guys in the industry with probably the most experience, if not in the United States, globally, especially when it comes to additive manufacturing in the medical space. And I'm sure along your journey, which we'll touch upon within this podcast, there was a moment when you realized, oh, this technology is more than prototyping. Can you talk me through your journey into additive manufacturing and touch on that point?
Thank you for the intro, but probably not the most experienced, but I've been around a long time, so I have a lot of it. So I started in the additive world actually back in the early to mid 90s in the plastic side of the business. So I was trained on stereolithography, went through all the hands-on training for that, and actually was using the technology very often for prototype development for our orthopedic or for our medical customers, not necessarily orthopedics, but a lot of customers when I was working with Johnson. And the problem with the plastics, you could create a really nice part very fast. You could clean it up. You could generate a almost precision looking part, hand it to a surgeon, and the first thing they would do was push a button, squeeze a handle, or drop it, and it would be pieces, right?
Yeah.
And so it became very frustrating all the time you spent putting this together to create a hands-on model that would just be destroyed in seconds, right? So in 2003, I started working for Morris Technologies. At the time, Morris Technologies was a small contract manufacturer, mainly in the plastic space. They had stereolithography, a few machines, and I was brought on to run their medical business. At that time, Greg Morris had found out about a technology in Germany called EOS, which was a metal-based additive manufacturing process. And in 2003, we brought the first additive EOS machine to the US. It was an M250. And it was great because it actually did what I call metal SLA, right? It allowed us to generate three-dimensional parts of metal that if you drop them, they wouldn't shatter.
Yeah.
But with that came some unique dynamics that you never really thought about, right? Because you've got metals. At the time we had I think it was like a ductile steel and a bronze-based material. And no one really understood about the attaching the part to the build plate and putting supports on it. And the support structures at the time were not conducive to easy removal. And you spent more time trying to remove the supports than it took to build the part.
Wow.
But you had a metal part that wouldn't break. So at that time, we looked at that to say, how can we use this technology for parts instead of what we were originally going to use the product for? And that was mold inserts for the injection molding field. And so we started making parts on the medical side, on the aerospace side. And then every finding that we had, we would actually give back to EOS and say, hey, can you do this? Can we do this? And then emerged the M270, which was a major breakthrough in the technology. It allowed us to use different materials, especially cobalt, and then eventually titanium, and then as it grew from there to other materials. But it really revolutionized the industry for us. And we were as I called it, kick the tire, raise the hood, let's see what makes the machine break, instead of saying, okay, the manufacturer said we can only do this. No, let's try this, right? Let's try that. And that's what really caused Morris Technologies to become on the face of the map on additive, is we were willing to try just about anything to make sure we got a quality part.
Super interesting story. And yeah, maybe you're not the most experienced guy in additive overall, but definitely in the top when it comes to metal additive manufacturing in the United States, since you were one of the first users of metal additive really in the
Right.
States. And what I think is very interesting is you'll never hear Chuck say, let's print a part. You refer to it as growing,
Grow
which I
apart.
think, yeah, you always refer to as growing, which I think is such a perfect description to the manufacturing process using AM. Now, we talked about the history of yourself, but also of additive, metal additive, especially in the United States. Where does the medical industry stand today when it comes to adopting AM?
Of the top five orthopedic manufacturers today, the OEMs, every one of them are utilizing additive manufacturing on the metal
Mm-hmm.
side and the plastic side. It is becoming a little bit more received by these customers. They are looking at it to where they can take this technology into the future, not only from an implant market on the orthopedic side, but also an instrumentation market,
Mm-hmm.
looking at custom instruments or being able to change unique features on devices quickly for one-offs for specific surgeries. So it's the adaptability is growing, and I think that has a lot to do with the fact that they're becoming more trusting in the technology, that it is a viable technology for manufacturing and for production. Now, saying that, and I had a unique conversation with our CEO at Morris at Tecomet 2 weeks ago, I guess it was, in
Mm-hmm.
regards to saying it is a development technology that we can use to make production parts. And the reason I say that is we still don't know a lot about this technology. We're learning every day, right? The fact that you can grow a part and you can grow it 100 times and be successful, and the 101st time you grow it, 101st time you grow it, it fails. Same build parameters, same program, same setup, same machine, everything, right? And it's not that it's a failure in the technology, it's just understanding the uniqueness of the technology, right? And so if I were to qualify the technology based on the human life cycle, we're not at adolescence, we're not at puberty. We're, to me, we're probably in the ninth trimester of birth because we're still learning. And some people might say, oh, no, it's definitely a production technology. And you can do production with it. But because the fact that every geometry is unique to itself, it lends itself to being a development technology that you can do production on. And we
Mm-hmm.
do production every day on our machines. We do. But we also do development every day on our machines, right? And every new geometry, we set it up, we support it like we think it should run, and we run it. And if it runs, great. If it doesn't, we go back and understand why, do a root cause analysis. Maybe it's support structure, maybe it's the way the recoder hits the part. It could be a lot of different things. So we go back, reevaluate what we did, make the changes, and start over.
And it is interesting that you say that. If from an outside perspective, people might be almost shocked that you say that baby is not even born. It's in the third trimester. But ultimately, that's a really positive thing because it's not even born yet, and we're producing serial applications on that technology. In the medical space, as you say, the top five orthopedic organizations are using metal and polymer AM for production parts. The automotive industry is ramping up. Space is using it on a daily basis for critical applications. So that truly means this is just the beginning of a very exciting journey. And I think
Absolutely.
the adoption hasn't even started to really hit those numbers yet that we're going to see. Now, when it comes to Tecomet, the organization that you're at now, what's the role that Tecomet plays in the orthopedic market, and what role does additive play for you guys?
Tecomet is the largest contract manufacturer in the orthopedic space today.
Mm-hmm.
We are probably 95% subtractive with 5% additive. And does that mean that we're not really pushing additive? No, we do push additive, but we've always been a subtractive company. I think the numbers I heard, we produce 70% of all femoral implants today through across our businesses, and we do 55% of all hip stems today. So we're a very large company on the subtractive side with investment casting and machining and that type of application. But on the additive side, we started in 2015. We have slowly developed the technology internally, getting with our customers and creating unique opportunities. But in this industry, and as I was explaining to you the other day, we have a particular product that we manufacture today, and it is in production. But it has taken us 7 years to get to production.
Wow.
Now, it's not 7 years of development. I say the development was probably less than a year and a half, maybe 2 years max. But it was getting the OEM that we're working with to accept the technology.
Mm-hmm.
That was the biggest impact. And that's just one case. Other cases where it took us 3 years to get into production because we had to develop the process. Where the current production project we're working on now, it has 165 SKUs, and they're all different. And you can't look at each part. You have to look at each part. Let me say, you have to look at each part independently of how you grow it, how you support it, and how you run it, because they're so unique. And so it's that development cycle that takes a while. Now, you mentioned all these other people in production today. Absolutely. Once you nail down the build parameters and get a project running, so let's say like the fuel nozzle, right?
Mm-hmm.
It's running in full production. It's doing great. But I would ask the question, when GE went from the M270 to the M280 on the production of the fuel nozzle, there was a major delay because you couldn't just take it from one machine to the next without redeveloping that process. When they went from the M280 to the M290 to the concept laser machine, the same process happened, right? Just like today, if you go from an M290 to an M400, it's not like you're taking the same program and sticking on that machine. You have to
Yeah.
redevelop it. So that's why I'm saying it's constantly changing. Yes, you can do production and you can do production repeatably, but there are some hiccups that you have to go through. Now, if on the subtractive side, if I go from I'll just throw out a machine, a Haas VF2 to a Haas VF4 or VF6, I don't really have to change how I set that part up and how I run it, right?
Mm-hmm.
Even though I'm going to a larger platform machine. But on additive, you do,
Yep.
because they're unique. And the technologies we're running today, the technologies that are developing product for production, I truly believe are not going to be the same machines we're running in 10 years. The technology is
Yeah.
going to change. Something is going to happen. Someone's going to find something out there, some unique capability that's going to change the whole dynamic of how we're doing it today.
Yeah, that's a good point. And I think the reason why we find ourselves having to look at a process from one system to the other is also because the process is very complex compared to machining, right? You're creating a part out of very fine powder particles between 20 and 60 microns in size, and you're using a laser to melt these particles in a very small and defined space of a laser spot size of 80 microns. So the control that you need in order to create a reproducible process is quite extensive. And here I totally agree. The users and the organizations that are using additive manufacturing truly require that experience to build processes and understand the system in depth. Now, you talked about a few of those programs that you guys are working on right now. One took 7 years, one took 3 years. Can you take us through that development lifecycle from truly idea or kicking off a product like this to production? Which steps is Tecomet taking to get there?
I think the biggest step is convincing the customer that this is the right application. I think that's the biggest step, and that you have the infrastructure to support that need, right? But it's not just from the additive side. You can grow parts, and there's a lot of companies out there that are growing parts. But once you grow that part, do you have the back end infrastructure to support it? And that's the post processing, the ability to remove the support structure, the ability to clean up the surface roughness of the part, the ability to meet the print requirements for that production part, right? Now, I will tell you that in my experience, and I think this has made it very easy for people in the industry, is that most people that do production today actually post machine the critical features after the parts are grown, and they don't try to dial in, as I call dial in, the features on the part to an as grown condition, which you can do successfully, right? As you look at the, say, the M290, and you do a analysis of the dimensional integrity of the part based on location, what we have found is that because of the laminar flow and because of the laser off of the mirrors and whatever, that the back left corner of the M290 yields the worst dimensional integrity. Now, I'm not talking it's hundreds of thousands of off, but it is not as tight a tolerance as what I'm getting in the 4-inch area from the center of the part. And as you look at the corners, you have some variation. But if your near net shape is going to be machined, it doesn't matter. If the features that are not machined and are grown as condition aren't dimensioned that tight, it doesn't matter, right? And so you look at each part that way, and you determine that if you've got a post process, and let me throw this in there as just a caveat, is that additive manufacturing is not going to replace subtractive manufacturing
Agreed.
anytime soon. You need that post process and that back end subtractive business to make additive successful, right? And so when we look at our products and we develop them from concept all the way through production, we have to look at every application of the product, right? You know, can it be grown? Can it be grown successfully? Is there repeatability? Do we have the post processing to meet the dimensional requirements of the part? Do we have the post processing to meet the finishing requirements of the part? Right?
Mm-hmm.
And today, I would tell you that's ever changing. The machining application, which makes you additive so unique, is I have the ability to grow holding features on my additive parts to make it easier for our back end subtractive people to hold it, to register it, to be able to get that repeatability from machining it.
Mm-hmm.
And in the past, this wasn't looked at. We would grow a part, we'd throw it across the fence to the subtractive guys and say, hey, you figure it out. And now we have the ability to do that successfully. If you wanted to grow a dovetail feature on the part that you could put it into a dovetail vise on your machining center, you can do that. And I think that's what's really helped the technology move forward, is that you can provide applications to the product to make it easier on the back end. Now, the other side of that, you have to understand the support structure, because again, if it takes you more time to remove the support structure than it does to grow the part, it may not be valuable for this technology.
Sure.
Right.
One critical piece, especially when we talk about the medical industry, is to ensure that there's no powder particles left on an orthopedic implant, for example, before it goes into a human body. There's also other industries where that is super critical, where you don't want metal powder, for example, to be trapped in an oil cycle in an engine or similar applications. Do you have any advice for people out there on how to ensure that there's no trapped powder particles within an application?
Now, that's a really unique question. I think that, first of all, you have to be very cautious about trapping powder, right? You have to make
Mm-hmm.
sure that there's no residual powder in the parts. And we've looked at this many ways throughout the years, doing a ultrasonic bath with high pressure flow against the part, and trying to get it to come out. To today, we actually have a vibratory chamber that was developed by one of the first companies that had a approved 510K approved acetabular shell that
Mm-hmm.
with porous structure. They developed this for the industry. They developed the chamber that once we bring parts out of the machine, it goes in this vibratory chamber. It goes in there for a specific cycle time to just shake the heck out of the parts while they're still in the build plate.
Mm-hmm.
And then that build plate goes through an ultrasonic bath with a high precision, high pressure um, flow on those cups, individual cups as it is. And then they go out for heat treat. Now, what we have found that what particles aren't removed through that process, that if you do your heat treat cycles correctly, they will solidify that powder. Now, if you don't get all the powder out or the majority of the powder out, it can affect the density of your product for a lot of structure.
Mm-hmm.
But we feel very confident that through the proper heat treat cycles, that you're going to center any residual powder and make it part of the solid substrate and not have to worry about it after that. But you have to go through those previous steps to get there.
Interesting. Thanks for those insights. I think a lot of people are wondering, especially while entering into this technology, that is something that's on top of their mind. Now, when we look at the medical industry today, we said it's that unborn baby that is about to be birthed.
Mm.
Nevertheless, additive manufacturing and medical go perfectly together, and the medical, especially orthopedic space, is actually one of the first adopters of additive manufacturing for production applications. And a month ago or so, we met in Austin, and you talked about some stats on how many hip cups today in the industry are actually 3D printed. Do you remember some of those numbers, just for the listeners to understand the scale of even current adoption of additive in that space?
It's about adoption. And this is actually, if you listen to a lot of the experts in the field that are doing projections for the future, today I can't tell you, maybe it's 25% of cups that are generated,
Mm-hmm.
but the experts are predicting that in the next 5 years, over 50% of all acetabular shells with pore structure will be additively grown.
Wow.
Now, that is all based on just how way the trend is going. But
Mm-hmm.
I think that as the medical OEMs understand the technology, feel comfortable with the technology, I think this trend will occur as the adoption of the technology has over the last, what are we at, a 30% growth over the last 5 years. And they expect that to be somewhere between 15 and 25% over the next 5 years. And that's just in the medical space. Today, there's an estimated 800, I think it's 880 or almost 900 additive machines just in the orthopedic space.
Mm-hmm. Mm-hmm.
And that's across all of the different players that are out there. There are roughly 600 of additive manufacturing or prototyping or development work done annually. And those are big numbers, right? And that's not probably anywhere near what's going on in the aerospace world. But I think as we adapt the technology moving forward, you're going to see these numbers grow. One of the projects that I was telling you about, the 7 year project that we were working on, that we finally got to
Mm-hmm.
production, it's 38 SKUs, and it is something that has been hand done or hand manufactured, subtractive manufactured for years.
Hmm.
And now we found a way to do it additively that gives us a more repeatable, more consistent part with thin wall conditions. And allows us to go into the general surgery field, not the orthopedic, but general surgery.
Hmm. Interesting.
And it's taken us into a new market.
That's the true power of additive right there, right? You're making it faster, more repeatable, better, and in this case, most likely also more economically viable than before.
And you have to be cautious on that. Let me interject here. You have to be cautious of the fact that just because it's better and more consistent, you also have to be cost competitive, right?
Yeah.
And there are some applications where if I can make a what I call a better part that is it's repeatable from a geometry standpoint, it gives you that pristine part. But if it doesn't bring value on across the board, then it's not a fit for this technology, right? If it costs us twice as much to manufacture, even though it looks better and it's more repeatable, it's not a value add, right? So I want to interject that and just say we also have to be very cautious of if we're going to cannibalize subtractive manufacturing with this technology, we have to be superior in what this product brings to the market.
Hmm.
If
Hmm.
and to me, I just say this just from history. If it's comparable, so if it's cost wise, it's the same, the value across the board is the same, then I would go subtractive over additive. Just because
Yeah.
I know I have more history with additive or subtractive, I have more knowledge with subtractive, right?
And that really counts for every new technology that
It
enters,
does
right? If
absolutely.
whether I use artificial intelligence now as a writer and I try to understand if it's not faster, if it doesn't get me to my finish line in a better way, why transition? So I 100% agree that we need to find these applications where additive adds true value and it's not
Yes.
just a one-on-one substitution. And that value may lay purely in the supply chain for some organizations,
It may.
where with the current supply chain challenges that we see, additive is a viable technology.
Mm.
Now, I have one more question for you, Chuck,
Yeah.
and that is you mentioned that in your 7-year project, one of the most challenging parts of that was to convince your OEM that additive is a viable solution. Now, there's many more folks out there today that still struggle to understand or wrap their head around additive being a viable production technology. What are some of your key messages to those engineers, C-level guys out there, or operators that are still a little bit skeptical about the technology?
I use this, and so it, one of the sayings in the state of Missouri is called the show me state, right? And I believe that additive is that same application. You have to show me, right? You have to prove to me that this technology can meet everything that I need and more
Mm-hmm.
to
Mm-hmm.
convince them. Now, when I stated earlier that all five of the top OEMs in the orthopedic space use additive, they do. And some are in production. Most of them are going into production, but it's taken them a while. They've had it for years, right?
Mm-hmm.
Of the top 15, 10 of them either have the technology internal or are outsourcing that capability for production. So it's being accepted. It's just being accepted slow, right? Think about this. I was touching audiences in the medical space in 2003, 2004. J&J at the Pew at the time brought on additive in 2000. Zimmer brought it down into, I believe, 2009, 2010. But it was out for a while before that. And we were talking to them and we were showing them parts. And that's why I say you have to put a part in their hand and you
Mm-hmm.
have to be able to convince them and show them that this technology can meet their need. Now, that 7-year part, I think we failed as much on convincing the customer on that project as the customer was in adapting the technology. They sent us a model file that was their subtractive model file,
Mm-hmm.
and we grew that part, not really paying attention to what was the best application for additive, but we wanted to show them we could get a part in their hand. And we did.
Mm-hmm.
And without having any knowledge of what the post processing requirements or the finishing requirements of the product was, we made a part, we cleaned it up to make it look like a shiny part, and we sent it to them. Now, what we failed to understand is the application of the part. And when they got the part and the surface roughness, when if you look at an additive part and you have experience with additive parts, even though you can polish them up and make them look good, if you don't get down to the solid substrate and remove that surface roughness on the part, you're going to have, and I hate to use the word pits, but it looks like pits, right? And holes, and they look dark when you polish them. And then people say, "Oh, it's porous," and it's not. You just haven't cleaned it up. You didn't clean it up, and because we did not know that, and we put it in the customer's hands, they said, this isn't going to work for us," right?
Mm-hmm. Mm-hmm.
So we had to go back and actually take their product and make modifications to it so it was additive conducive, and to finish it to the point that their actual production subtractive part was, and then get it back in their hands and say, "Hey, this is what you can do with this technology."
Mm-hmm.
So we failed as much of not providing them with the final part because we didn't ask the right questions. And that's important. You have to ask the right questions of the customer to understand the application of their need. And once you do that and you understand that, it becomes more of a symbiotic partnership than a vendor customer relationship. And to me, with additive, that is the most critical thing, to be able to sit down with your customer and talk through what the product needs are and make those suggestions, recommendations to make it an additive product and to show the value to that. But also do not fear to push back on the customer and say, "This is not an additive application, and here's why." Now,
Sure.
people might say, "Well, you're turning away business." And I say, you're not really turning away business, because if you provide them with a product that does not meet their expectation, now you've changed their mind on if this technology is a value add for them or not. They look at it and say, "I got a lousy part. I'm not going that way. All additive parts are going to be like this." And that's not the case, right? So it's that relationship that makes it key to success. And the other thing is understanding and helping your customer understand the ability to design to the technology, because that's key to success.
Mm-hmm. Mm-hmm.
Understand the limitations of the technology. How do you do that? You fail. And I say this, and Greg, and this will probably make Greg Morris smile, but it's the case. Morris Technologies was successful because we failed, and we failed a lot. But every time we failed, we root cause analysis the problem, corrected it, came up with something new, unique, and moved forward. And that's how we became successful. And that's what you have to do with this technology.
Yeah, perfect summary to a really good episode, Chuck. Thank you for all the advice that you've shared with us today. I'm truly excited to see the future of medical in the space of additive manufacturing. Can't wait to see companies grow more parts and grow parts that we haven't seen before. And I can't wait to see what comes out of Tecomet next. So thanks for the advice, and thank you for being on Additive Snack.
I appreciate the invite to be on the show. And let me add one last thing in closing. Additive manufacturing is going to grow immensely in the future because we've taken it into academia, we've got it into the colleges, we've got it into the high schools, we've even got it into the elementary schools. And by getting this technology in the hands of the younger kids through education, this technology is just going to just flourish.
Couldn't agree more.